Hello everyone, and welcome to the second video in this lecture series. In this video we'll be talking about datum features, datum reference frames, and simulated and target datums. So what exactly is a datum? Well, a datum is a theoretically perfect surface, axis, plane, or point. So datums, the key here is that datums are theoretical and they are simulated. And what that really means is these are, so this for example is a datum plane, and it is a perfectly flat 2D plane. So the reason why we care about having or defining these within our drawing, within our model, is for one, it makes it easy to dimension off of and validate off of. So as we talked about in our first video, you have imperfections in physical objects due to the machining process. And you can just imagine how frustrating it would be if you were measuring off of edges on the surface itself, because your reference point is going to be shifted depending on the imperfection that you're measuring from. And it just makes everything really confusing. So the way that they do it instead is they define a datum, something like a datum plane, and they measure off of the datum plane instead. And what's really great about that is when you measure off the datum plane, you have a common reference point, right? And then all you have to do is account for the plus minus in the imperfection. So let's say that the maximum distance peak to trough is 0.05. That means that any measurement that you do off of this datum is going to be a common point, and you know that it's going to be at, and you know that the maximum tolerance from the imperfections is plus minus 0.05. So that just makes everything a lot easier, right? You're not measuring off of these peaks and troughs. You're measuring directly from this common datum, flat datum, perfect simulated surface, and then you just have to add in the imperfection range afterwards. The second reason why we use datums, why we define datums, is so that we have something to reference off of. And this will be a lot clearer in the later slides when we start looking at engineering drawings that incorporate these datums. But oftentimes you want to say you want this to be perpendicular to something, or you want this to be positionally located to something. That something that you're going to be referencing is often going to be the datum. And that's just because it is a good reference frame. It's a good thing to do reference off of. So those are two of the main reasons of why we use datums. So, we talked a lot about how datums are theoretical and they're simulated, but that doesn't do us a lot of good unless we can actually use it somehow, right? So that's when we get into how the theoretical translates into the physical. So physically, we can represent these theoretical surfaces, these theoretical planes, these theoretical axes with these items. So parallels are intended to represent datum planes. What you have here is essentially two very accurately, very precisely machined items that are pretty much, this is essentially a perfectly flat 2D surface. And so is this. So you can say that, this is the equivalent of your datum A, and this is like your datum B. So that's how you can physically represent the datums, and how, like, inspection, what they might do is they might pull out these parallels, and then they might take measurements from the parallels because they represent the datums in this case. So that's a datum plane. But let's say that you define the datum axis. How would you physically simulate that? Well, that's why they have these things called gauge pins. A machine will find the axes of this precisely machined datum pin, and that will physically simulate the datum axis that you defined, right? And now, if you want to measure off of this datum axis, well, that's easy because you have this physically created gauge pin to help you for the reference there. So here we were really looking at this plate, but let's say that we have a pin, right? And now let's say that we want to simulate the datum axis on the pin. So how do we do that, right? Because in this case, you have, this is what we call external features, right? We call them external features because something goes in them. So in this case, you're looking for a pin to go in here, and you're looking for like maybe I don't know, smaller pins to go in here. So if the pin is the internal feature, then the slot in which the pin fits into is going to be your external feature. So that's going to be your plate. And that's going to be external feature. So we've talked about external features. And now let's talk about what happens if you have an internal feature like a pin. So how do you simulate the datum axis physically for a pin? You can define it like this in a drawing, and that's how we say, well, you know, we want datum axis D to be the simulated datum that we can reference off of. But physically, that is going to be simulated by something like having a vise. What the vise does is it contacts this pin, and then it takes the midpoint between devices, and whatever that midpoint is, the midline is, that midline will then become your datum axis. So then this becomes datum axis D. So that's how you physically simulate the datum axis. So at this point, we've talked about, you know, how datums are theoretically perfect surface axes, planes, or points, and we've talked about how you can, you know, physically represent this by these measuring devices, by these precisely machined items. So, you know, a drafter defines the datums for the part that they're machining in order for the inspection people to actually have something that they can, you know, use to measure off of, so they know where to measure off of. And that's how you kind of relate, you know, the theoretical idea of the datum reference frame with the physical datums themselves and with the inspection criteria. So another thing I just wanted to talk about here quickly is, so we talked about, for instance, how you have a parallel and you have a plate. So where exactly is the datum, right? So this gives you a better idea of what we're talking about here. You can see that the orange represents the surface of the parallel. And you can see that this surface is finely machined, and there's very little, I'm going to say something like plus minus 0.0001 surface roughness, but the plate itself might be a lot rougher, and this might be something like plus minus 0.05. So the physical datum plane is defined by the location where these two objects are going to be in contact with one another. So if this is the parallel, and if this is a plate, then this midplane here, this contact line is going to be your datum A. So that just gives you a more like in-depth look of what exactly is going on here, and how exactly does that define your datum A. So now let's look at some engineering drawings to actually understand datums better. A datum is represented by something that we call the datum feature symbol. the datum feature symbol looks like this, and it is essentially what defines your datum. So in this engineering drawing of the plate, we have a defined datum C, which means that, this line should be where datum C is created, and this line is where datum B is created. Sorry, these should be flat lines, I just can't draw a straight line. And this is where datum A is created. So physically what that looks like is you have a plane here, and then you have a plane here, and then you have a plane here. So that's going to be your A, B, and C datums, which, as we talked about before, can then be represented as parallels when they're actually physically doing the inspection. So now, if they want to verify that this is actually 5 inches, they're going to take the measurement from the edge here, and they're going to measure it all the way to datum plane C, right? And that's basically the idea. If they want to measure it from here, same thing. They're just going to measure it. They're always going to measure it to the datum target, to the datum plane, and not to the actual surface of this part itself, because the actual surface is rough, and it's impossible to get a consistent measurement, if you're measuring it to the actual surface itself. So this shows us how datum planes are defined. But what if we want to define something like a datum axis, for instance? Well, it's a very similar concept. Datum planes, you basically put the datum feature on the surface in which you want the datum plane to be created on. But for datum axes, well, datum axis, you just tag it on to the dimension of the dimension of the feature that you want. So for instance, this whole feature is defined by this dimension, and then by tagging on this datum feature symbol, you're saying that this datum axis here is going to be datum C. That's essentially what that is saying. And then we do something similar here, except we say this one is datum B. And then physically how that looks is the gauge pins. So as we talked about, this becomes datum B, and this becomes datum C. We want to physically simulate those datum features, the datum axes that we defined here. Alright, so now we're going to explore some of the nuances of the datum reference frame. So up to this point, we've really talked mostly about datums. We've talked about datum surfaces, datum planes, and datum axes. A datum reference frame is basically the combination of all of the datums, or not all of the datums, but let's just say a set of datums which fully defines the location or the orientation of a part. So what do we mean by that? Well, we said here in the slide that we have 3 different datums defined for this part, A, B, and C. And you can see that with defining these 3 datums, we are essentially fixing this part. So the orientation of this part is fixed because it is constrained by the datums itself. Because we're saying that this surface has to be in contact with datum C, this surface has to be in contact with datum B, and the bottom surface has to be in contact with datum A. So now this part cannot rotate, it cannot translate, it's fixed. And it's very easy now to measure and to do what needs to be done for inspection. So the datum reference frame is how we define the orientation of an object for inspection. So we remove all the degrees of freedom by defining the datum reference frame. And typically, the first datum in the datum reference frame is going to be called your primary datum. The second datum is going to be called your secondary, and the third datum is going to be called your tertiary datum, which is what we talked about here. And the reason why this matters is because this defines the order of operation in which these datums are physically aligned to. So if you have this plate, right, the first thing that the inspection guy is going to do is he's going to put this plate on datum A, and that's going to fix the up and down and the rotation aspect related to that datum. So once that is fixed to datum A, then he's going to fix it to datum B, and afterwards he's going to locate it to datum C. So it goes in order. It goes primary to secondary to tertiary. So you might be wondering, why does it matter? Like, why does the order matter? Why can't you go from tertiary to secondary and then to primary? Well, the reason why the order matters kind of goes back to the idea of, one, you have imperfect surfaces, and two, because you are using these datums as reference and as a way to measure dimensions. So to get an idea of this, let's say that we have this let's say that's a cross section of the plate, and this is the ideal case where there isn't any imperfection along the surface. Now let's say that this is that same plate, but I've exaggerated the imperfection. And now what I'm going to do is I'm going to orient this plate along the datum reference frame. So if I define this as datum reference frame B and define this as datum reference frame C, well, when I orient this, what's going to happen is I'm going to first orient it along B, and then I'm going to orient it along C, and this is how my part looks when I'm going to begin measuring. So now let's say that I have this guy, and once again I have my C, and once again I have my B datums. But now let's say that I orient it to C first, right? And then I orient it to B. So remember, this is a very exaggerated plate, right? So this is how it should look if it was a perfect plate, and this is how the imperfection kind of made the plate a little more slanted than what it should. But we oriented it in two different ways here, right? In this case we did B then C, and in this case we did C then B. But here's a crazy thing, which is that when you do the measurement, right, let's say you want to measure this point to datum C, and you want to measure this point to datum C, you can see that you're getting two different measurements here depending on how you did the orientation, whether you orient to B first and C, or you orient C first and B. So this might give you 0.05 as the distance here, because remember that we always measure the distance relative to the datum itself and not to the actual edge of the part. So this might give you 0.05 for that point, and this same point on the same surface, this might give you 0.03. And this is two different measurements, and it's not clear which one is correct, right? And that's a problem, because we should always be clear on how to measure something and which one is effectively the correct measurement. So obviously this is a very exaggerated case, but it shows you why it matters that the orientation of the datum is defined accordingly. So as a drafter, the datum that you define as primary datum should always be the one that is the most important datum. Secondary should be the secondary most important datum. Tertiary should be the third most important datum. And because the way that you define it does affect your measurements, it's always important to kind of keep this in mind. Like which surface, which point, which axis do I care about the most for measurement purposes, for reference purposes? That should be the one that I define as a primary. And then I move on to the secondary, and then I move on to a tertiary. So because in this case, I'm saying that I want B to be my secondary and want C to be my tertiary, this is not correct. This is doing it in the wrong order. And, this is the correct way of doing it based on how I defined my datum reference frame here. So the final thing I want to talk about here is defining this datum reference frame. So we've said that having 3 of these datum planes, datum plane A, datum plane C, and datum plane B, effectively defines your datum reference frame. The idea with defining a datum reference frame is that you want to remove your 3 degrees of translational freedom and 3 degrees of rotational freedom. So you want to effectively remove 6 degrees of freedom. So defining 3 planes definitely removes 6 degrees of freedom, but technically you only need 6 points defined on your object in order to remove your 6 degrees of freedom. So to illustrate that, we have this picture here. Your first 3 points that you define on a parallel surface, well, that effectively becomes your datum A. Your next 2 points on a surface that is perpendicular to datum A, those 2 points will define your datum B. And then finally, on the last point that you define, that point has to be perpendicular to A and B, but you only need to define 1 point, and that's going to be your datum C. So, that's always something that I found a little surprising, but if you think about it, it makes sense. Because you're moving 6 degrees of freedom, you only really need to fix your part at 6 points, as long as they're, accordingly perpendicular to one another. So you don't necessarily have to define 3 different datum planes. All you really need is 6 points in order to define your 3 datums, and that will fully constrain all 6 degrees of freedom on your part, and at that point you have defined your datum reference frame. And so the reason why we sometimes use the points instead of using planes to define the datum reference frames is because you might have a lot of surface roughness along this location. So maybe you want to define your datum plane precisely at these 3 spots, because you know that these 3 spots are very smooth surfaces. So that's why we have datum targets. On a drawing, datum targets are denoted normally by an X mark, or they're denoted with a circle. And what this tells you, you can kind of correlate this here. These 3 points are, that is these 3 points, right? And then these, and then these 2 points here, well, that's going to be, these guys. And then finally, your last point here, well, that's going to be this guy. So you can see how you define it on the drawing, and how that physically translates to define your datum reference frame here on the physical part itself. So that's pretty much all I have here. Thank you for tuning into this video, and stay tuned for the next. Thanks.